So welcome to the presentation of my solution, my colleague's solution to the challenge. So our approach is based on a sequence-to-sequence model. It's a pointer generator. They call it a model pointer generator, and it's from a paper of C et al. So this paper is about maybe 2 years old. So yeah, it's end-to-end learning. So we want directly from the summary to generate directly from the input article to generate the summary. And we do not use any additional data as the one that is the data set that was provided. Now, here in this talk, I want to talk mainly about two issues that we found while using this model. The first one is repetitions of words or phrases. So with this sequence-to-sequence model, it can happen that, as in this example, we have some words or tokens are repeated. So for example here, it basically says the same thing twice. It says Landesmuseum Hannover ist ein Landesmuseum, which, yeah, it says it in the name. So we would rather not have this in the summary. And then the second issue that I want to talk about was spectral corrections. So sometimes the model just makes things up, and we clearly don't want that. So for example, in this sentence we have Tilka Kapskink ist ein Schmetterling aus der Familie der Ernährung. So first of all, it's not a butterfly, it's a lizard. And the second, Familie der Ernährung, family of nutrition, doesn't make so much sense. So these things we want to avoid, if possible. And here I want to go into a little bit of detail how these issues are tackled in the model and how it actually works. So let's look at the system. We are using a system that looks like this. So first we do some pre-processing on the data. This is some standard things like tokenization of the articles. We reconstruct a vocabulary. We use not subtoken. We don't do subtokenization, so we use like words for tokens. And the vocabulary is 60,000. And we use fast text embeddings for the tokens. Then the main part of the system is the sequence-to-sequence part. We will have attention, we have pointers, we will see what that means in a minute, and then we have the coverage mechanism. This mechanism helps the model to avoid repetition. Then up here we have an additional encoder. This is the fact encoder, and it will help to encode facts from the article and then guide the system to actually produce correct summaries. And then lastly, we need to do some post-processing. So as we tokenized the articles before and lowercase them also, we need to detokenize them in the end and also capitalize some of the words. In German, for example, nouns are capital, so we need to take care of that. Okay, let's first talk about the sequence-to-sequence part of it. So this is the main part of the model, and here in red we see the encoder, and we encode only the first 400 tokens of the article. And then once we did this with the bidirectional LSTM, we are ready to start decoding. So this is the yellow, these are the yellow bars on the right. So each word of the summary is produced one after another, based on the encoding of the article and based on the previous tokens of the summary. But how do you know which words to put? We know this by producing a vocabulary distribution. So this is just a softmax over all the, like a distribution over all the words in the vocabulary. So if we had this example here, A beat has the highest probability in this example, so maybe we just put this as the next token in the summary. Now, where does this distribution come from? Two things are the input of this. The first one is the last token, or the representation of the last token of the summary that we already produced. And the other input is the context vector. So what is the context vector? As the name says, it captures the information of the context of the article. So this we also call the attention mechanism. And what it does, it helps the model to focus on certain parts of the article. So in this case, it looks like victorious or win are the parts where it focuses on. So this might also be the reason why beat has a high probability. So from here, we are ready to see what about the pointers. So what are pointers? They are essentially pointers to the inside of the article. They let the model just copy some of the words directly from the article to the summary. So why is this a good idea? It helps a lot with out-of-vocabulary words. So 60,000 might seem like a lot, but it's not so much, because in German we have many compound words, we have many names of entities and so on, which are not in the vocabulary. And it's really important that these words also can occur in the summary. So we just copy them to the summary. Okay, let's see how these pointers work. And they work as follows. So this is the same as we've just seen before. The green distribution is the vocabulary distribution over all the words of the vocabulary. But now we add the attention distribution. So the attention distribution are the blue bars over there. It's the distribution that says where to look inside the article. So if like this this word over here has a high probability, then we add this to the corresponding word on top of the green one, and then in the final distribution, the sum, it gets an even higher probability. So then the model might choose some words that only occurs in the article and not in the vocabulary actually. Because if it does only occur in here, it's no problem for us to just add 0 up here. Like if we only have, so we can only just add 0. The blue or the green can be 0, so that's no problem. And then finally, the model is able to learn how to weight the two. So sometimes it will prefer to copy things from the article, then the blue one will be weighted higher, or sometimes it will learn to rely more on the vocabulary. So the green one will be higher. So this Pgen is just a coefficient that weights the two, which is learning. Okay, let's get into the first issue that I want to talk about. It's repetitions, and for that we have the coverage mechanism. So this is not our idea, this is also from this paper, I'll say it now. So what are we looking at? On the right we have 4 tokens. Let's imagine the article only has 4 tokens, A, B, C, and D. And then for each time step in the decoding, so for each word that we put into the summary, we get this attention distribution, the blue one from before. And what we do now is we just sum up all the values in the attention distribution per token. Okay, so why does this make sense, or why should we do that? Because this keeps track of which words are frequently attended to. And now we can use this coverage vector as an additional input to create the next attention distribution. So the model might learn to not attend to the same place several times, and by doing so, learn to not produce the same words all the time. So we don't have repetitions. That is the goal. And second, the authors of the paper found that it's also a good idea to include this coverage vector as an additional term in the loss function. But yeah, let's maybe not discuss this too much in detail. So let's just look at an example. So in this example here, no coverage. We had the LB-Hafen Brunsbüttel GmbH twice. And now in this case, the coverage actually seemed to work. And we only have the Hafengesellschaft Brunsbüttel GmbH, which refers to the same thing only once. So in this case, it worked. Okay, let's get to the second issue that I want to talk about, factual correctness. So this might be even more important because yeah, fake news with the discussion of this is also like really relevant. So this was important for us. What we want to do is we want to extract facts from the article and then feed these fact description to a second encoder here on top. So this is also just an LSTM, a standard LSTM encoder, like the other one that we talked about. And then it's just left to combine the information of both encoders and feed them to the decoder. Okay, let's see an example. Oh yeah, this is also based on a paper by Cow et al. But they have it a bit differently than we have. So what is a fact description? Fact descriptions are on a sentence basis. So first, what we do is we do dependency parsing. This gives us a graph, and from this graph, we can extract tuples. And we are interested in tuples, subject, predicate, and predicate object. Here, for example, the blue one, if we see in the sentence, it says bildeten sich Bündnisse, and from this, from the dependency graph of this, we then extract Bündnisse bildeten and bildeten sich. Now, having these tuples, we can match the predicates and get triples from this. So Bündnisse bildeten sich would be the one from the blue one. And then finally, we found that it's a good idea, or that it helps to clean a bit the noisy tuples that we have, or triples that we have, by just discarding the ones that do not contain a named entity. Because there were many, many more that were just not looking useful. Then finally, we just concatenate all the triples and get what we call a fact description here on the bottom. So this is also sentence-like, and we can feed it into the second encoder. Okay, now how to combine the encoders. Remember the context vector from before, it was part of the attention mechanism, and it was constructed from the attention distribution. So now we have two encoders with attention, then we also have two of those context vectors. And what we do is we just combine them together. Here are the formulas. So maybe on top here we have GT. GT are coefficients that allow for a linear combination of the two. And then we end up with just one context vector, again, as before. And we just give this context vector to the decoder. So from the point of view of the decoder, it looks essentially the same, but it can learn to attend to the fact more, or to the actual article more. So one more advantage of this fact description thing is that we only have 400 tokens in the real encoder. So this fact description are also limited to 400, but they might range longer inside the article. So this is a little bit also might help. Okay, so here are some examples that we got. Yes, mostly they seem to look acceptable. They are definitely relevant to the article. They are in most cases fluent. But sometimes we still have problems with repetitions. Sometimes we still have problems with fake or wrong content. So the things that we talked about here, they help, but they do not solve the problem. And yeah, I don't have root scores here, but you saw before, root, yeah, it seems to be alright with this approach. So where to go from here? So this work was actually, this system was developed for news articles. For Canada, we tried to generate headlines for news articles. So for Wikipedia articles, we just applied the model that we had with some modifications. But we did not look into how Wikipedia articles are structured. Maybe there is some stuff that we can use there. So this would be an idea. And then bad effect extraction, for sure. Because for English, there is a tool that gives you the triples directly. We didn't have that for German, so we had to fall back on a quick homebrew solution. And then more data, because 100,000 is maybe not so much. There should be more possible with that. Okay, so that's it. Thank you for your attention.
Yes. Have you thought of a way to fact check after generating the summary, so as a post-processing step?
Yeah, so we had some ideas about taking phrases or parts of the summary and then check if they occur in the article. But the problem is that maybe it will be, like the content will be similar, but the phrasing will be different in the article, so it's not that easy. And in the end, we didn't find a good way to do it. Yeah. But yes, there should be. This is something we don't have. Okay. Anything else? Yes.
What was again? Did you have evidence that this fact module actually helped, or is that based on your analysis of the data, or?
So we don't have actual numbers. Yeah, that's a bit the problem. But by looking through the results, we thought that it would work. So yeah. So yeah, the paper that did this in English, they also didn't find a good way to do this automatically. So they had, I don't know how many people, but they did manual evaluation of the thing. And I'm not quite sure, but I think that in 80% of the cases where they had fake news, so to say, they were able to improve it by their fact model. But yes, as I said, in German it's a bit more difficult because the fact extraction seems to be more difficult in German. Okay.
Good, thanks a lot.
Thank you.